In this video, we're going to talk about calculating Gibbs free energy and what Gibbs free energy is. And I say that as if Gibbs free energy is an easy thing to understand. Okay, Gibbs free energy, for me, is a little bit difficult to understand what it actually is. Like when we talk about enthalpy and heat transfer, like that kind of makes sense. You kind of see it based on the temperature changing and things like that. For entropy, I think that entropy is the most concrete of all these examples. Like we get that, or of all of these thermodynamic values, because we can see or we can understand that molecules are moving around, and as they move around, the more that they move around, the more entropy they have, things like that. But Gibbs free energy is really kind of a harder thing to understand. So I'm going to avoid any sort of like physical, trying to make that into a physical meaning for what entropy is. And I'm going to just say that Gibbs free energy is a measure of spontaneity. If you see any question that asks if the reaction is spontaneous, the question is really asking you, what is the delta G of the reaction? Okay, delta G is the symbol for the change in free energy. Okay, and so if the reaction has a negative delta G, that means that the reaction is spontaneous and it will go without any outside help toward the products. Okay, that's what that means. If the delta G is positive, and the sign of the delta G is positive, that means the reaction is not spontaneous and it'll just sit like a bump at a log at the reactants. It will not go forward. And if the delta G is 0, if it's calculated out, that means the reaction is at equilibrium. And fortunately, we're not going to spend a ton of time relating Gibbs free energy to equilibrium, but there's a whole huge kind of interesting analysis that we can do that relates Gibbs free energy to equilibrium, but we're just not going to do it here. But there are a few ways to calculate free energy. We can do this in a couple of different ways. The one, and kind of the least common, make sure you hear what I'm saying, the least common way is if we're given the delta G of formation of the reactants and the products. And then we can use kind of the typical thermodynamic calculating strategy and just do delta G of the reaction is the delta G of formation of the products minus delta G of the formation of the reactants. Okay, that happens, but not as often as this next equation. Okay, and so the thing that happens here, okay, is really how we calculate delta G most of the time. Okay, delta G naught equals delta H naught minus T delta S. Okay, and that's really what we're looking at. Okay, and so this tells us how those reactions that we've determined that are favored, products favored, reactants favored, can be spontaneous. And it also shows the temperature relationships. So that's three things that we're worried about. Okay, and so we have delta H, the enthalpy, delta S, the entropy, and then the temperature. Okay, and so that's what makes this so powerful, is that enthalpy, a reaction that is enthalpically favored is exothermic, and a reaction, so that means it has a negative, and a reaction that is entropically favored is going to have a positive delta S, and you can see that the math of that works out. What's a negative minus a positive? It's an even more negative number, and so no matter what the temperature is, if you have a negative delta H and a positive delta S, it's going to be spontaneous at all temperatures. So let me kind of get rid of this thing here, and we will, okay, we can see. Okay, let's see if I can, so this shows delta S. If delta S is positive, okay, that means that and then the delta H is negative, that means the process is spontaneous at any temperature. Now let's flip-flop that. What if the delta S is negative and the reaction is endothermic? The delta H is positive. That means no matter what temperature you have, the process or the reaction is going to be non-spontaneous. And I think that that's important to note too. Now, the two that are very interesting is when the signs of delta S and delta H are the same. As my voice cracks and I finally hit puberty. It's the same. Okay, no, but when the delta H, the sign of delta H and delta S are the same. Okay, so here, if they're both positive, that means that, well, positive, positive, that means that in order for this to become, in order for delta G to become negative, this term here, the delta S term, has to get big. If this is positive and delta S is positive, that means that this is going to, this whole term is going to be positive, and in order to subtract something that is going to make the overall value negative, that means that this has to be a large value. So that means that this process is only spontaneous at what you can kind of read. It says high temperature. Okay, well, that's one thing. Well, now what if instead of both of them are being positive, what if both of them are negative? Well, that's what we have here. Okay, well, the process is spontaneous at low temperatures. Let's look at the math of that. Well, this is negative, and then this is negative. Well, at negative minus a negative, that's going to be plus a positive. So this is going to, at low temperatures, that makes this term very small. And so that means that a negative plus a small value is still going to keep that negative. Okay? But as the temperature increases, what's going to happen eventually is that delta G is going to become 0. It's going to reach equilibrium. It's not going to react. And then it's eventually going to go to positive, and it will not react at all because the reaction is going to go from spontaneous to at equilibrium and all the way to non-spontaneous. And that's what we're implying here for this in this box here. Okay? So this box kind of is the be-all and end-all of what delta G is and what it means. Okay, so let's do an example. Okay, so it says calculate the free energy change. Okay, free energy change, just to let you know, is delta G naught for the formation of methane from carbon and hydrogen. Okay, so here's C graphite, okay, and then H2 gas. Okay, so, well, in order to do this, notice the values that we're given are not delta G's. We have a delta H and we have S naughts. So that means the formula that we're going to use is delta G equals delta H minus T delta S. Okay? So in order to do this question, we actually have to calculate the delta H and then the delta S and then plug it in to find the delta G. So this is one of the reasons why I like delta G as a problem, because it kind of shows how to do all the thermodynamics, all these delta H, delta S, delta G. So let me let me get this onto our little scrap paper or on my tablet, and we'll work through the problem. Okay, so I've transferred all of the data to my tablet, my little worksheet here. So let's do this. So we're going to calculate delta G, but in order to do that, we need delta H. Okay, so the delta H equals, and this is how I'm going to eventually just abbreviate it, products minus the reactants. Okay, so what is the products here? Products is, make sure this reaction, no, it's not balanced. Okay, good. Now I'm going to balance. So I balanced it. It has to be balanced. Remember, the coefficients mean something here. So the products, so it's 1 times this guy, negative 74.9 minus reactants. Reactants, 0. Sorry, not 0, 1 times 0 plus, let's see, 2 times 0 Okay, and so now we do this. So this is delta H is negative 74.9 minus 0. So now the delta H equals negative 74.9 kilojoules. Okay, now we do the delta S. Okay, so we do it the same way. Delta S naught equals products minus reactants. Okay, the products, there's 1 mole of product, and the delta S is plus 186.3, okay, minus 1 carbon. And now the delta S, or the S of carbon is 5.6. 5.6. Oops. Whoa. Plus, because we add up all the reactants, plus 2 times H2, and H2 is 130.7. 130.7. Okay, and so now this is 186.3 minus, let's see, 5.6 plus 2 times 130.7. Okay, and that answer is 267. And so now we do 186.3 minus 267. And then that equals negative 80.7 joules. Okay. Now, so that's the first two parts, but now we need to calculate delta G. Delta G equals delta H minus T delta S. Now, there's two things to worry about here. The temperature that I gave you in this problem, temperature was 298. Okay, so that's already in Kelvin, but if it's not, you have to make sure it gets there. So this is the temperature equals 298. The second and probably more tricky thing that's not tricky after I point it out, but you also have to make sure that the units of the delta S and the delta H are the same. Notice that this is in kilojoules and this is in joules. Okay? That is a huge hurdle for students doing this, because when this happens, students forget to interconvert. So I always like to take joules and put them into kilojoules. It just becomes easier. So now this in kilojoules is negative 0.0807 kilojoules. I move the decimal point over 1, 2, 3. Okay, good. So, there it is. So now this just becomes kind of a simple, I say simple plug and chug, where we take our delta H, which it was negative 74.9 minus 298 times negative 0.0807 kilojoules. Now, this is one of those cases where the delta H and the delta S have the same sign. And so we want to know if delta G is positive or negative. So we're going to do that. So we're going to go 298 times negative 0.0807. And so there's that. And so now we do negative 74.9 minus that. And we get that the delta G is negative 50.85 kilojoules. That's what the question gets. So that reaction is spontaneous. That's what that tells us. It is going to happen without any outside interference at that temperature. Okay? So that gives us an example of how to solve for delta G, the Gibbs free energy.